Hello and welcome. Today we are going to be doing a problem from an exam from a couple of years ago. This is a dynamics problem. There's a bunch of things going on here, so I think this is a really good problem for practice. So I'll read it and then we'll go ahead and solve it. So we can see the problem here. We've got some people that are sliding down a roof that are attached to some pulley mechanism attached to some dinosaur skull. And so after a series of unfortunate events at a theme park, dinosaurs have escaped and are swarming the visitor center in which Alan, Ellie, Lex, and Tim are trapped. Luckily, they managed to find a window in the roof with a pulley mechanism rigged to the fossil display, which weighs 650 pounds. They have the idea to hold on to the rope and slide down the roof. The initial configuration starts at rest with 0 feet of rope between A and D and with 8 feet of distance between the pulleys B and C. The final configuration is reached when the fossil arrives at point C. The roof is at an angle of 55 degrees with respect to the ground. The coefficient of friction of the roof is mu is 0.4 and gravity is 32.2 feet per second squared. What is the velocity of the people when the final configuration is reached? Or so what is the velocity of the people when they reach the bottom part of the roof down here at D? And so a couple things that are interesting here. It's saying that there's 0 feet of rope when we're at the first configuration, when the people are up at the roof at A, and there's 8 feet of rope between C and D. And it also says that the configuration starts at rest. So any initial velocity we know is going to be 0. So let's look and see what we've got here. So first I've drawn a free body diagram. There's nothing in here that's not in the problem. So I'm going to start with this and then we'll work through, and we'll add in all the details that we have. And so the first thing I'm going to do is we see that there's some bones kind of on this pulley mechanism. So there's going to be some relative dependent motion here. So the first thing will be this velocity relationship that we want to identify. And so usually I reserve different colors for different ropes, but this is all one rope. And so in this case, I'm going to use my colors to also illustrate what we're going to be labeling as our different datum in this case. So we've got the one rope that the people are sliding down the roof. I'm going to draw that up here in blue. And so we can call this SA, or the position of A. We'll just call everything on the left, the people will call A, and then the bones on the right we'll call B. And so we see we've got this pulley mechanism, and I'm just going to color these red like this, and then we're going to call this SB. Okay, so we're doing all this, and really, I probably should put this before, but what we're looking for here is we're looking for V2. So what's the velocity going to be when our people get down here? So our velocity relationship, in this case here, we have the length of our rope is going to be equal to this distance here, A, or SA, plus, and we can see over here for B, we've got 1, 2, 3 lengths of B plus 3 SB. And so we've got SA, we've colored in blue, SB, we've colored in red. And so we can take the time derivative of these. So the overall length is not changing. So that's going to be 0. So we're going to have VA plus 3 VB, or in other words, VA is equal to negative 3 times VB. And if you wanted to go one step further, you could also say that the acceleration of A is equal to negative 3 acceleration of B. Okay, so we have our relationships up here. And so now we've got a relationship between our A and B's. We can call this equation one, because likely we're going to have some other things going on here, and we're going to need to know what are these different relationships. So the bones, it says the bones weigh 650 pounds. So we can add this here. And notice here for the free body diagram, I've just clumped the people all as one. We can treat the people as one body here. And the weight of these people is 200 plus 130 plus 65 plus 45 is equal to 440 pounds. Okay, so hopefully, even if you didn't know what to do here, how to approach this, we can at least start with this and we can get, some things going. And hopefully by now, we're going to be looking at these people sliding down the roof. We were given friction in the problem. So I'm going to draw a free body diagram over here of the people sliding down the roof. And so I've got my people here. They're going to have some weight. That's 440 pounds. The rope is going to be exerting some kind of tension force T. And so keep in mind, this tension force that the rope is exerting on these people is going to be the same tension all throughout this rope. So later on, if we need to, we could draw a free body diagram of this side as well, knowing that we're going to have three tension forces acting upwards on this pulley over here. We're sliding down, we're going to have normal force N, and we're going to have some kind of friction. Force of friction is going to be resisting it sliding down, so it's going to be acting upwards. As it goes down, it's going to have some acceleration because it slides down, call acceleration A. And because when I look at this, the only component here, I can add this angle if I want to. 55 degrees. The only component here that's acting not along the plane of the roof is this weight force here. So what I want to do is just define my y and x coordinates like this. So positive up the roof, and then perpendicular is the positive y. So our sum of forces in the y direction is going to be equal to 0. It's not moving in the y direction, it's only moving in the x direction. So in this direction, we're going to have n minus w. And so this value here is going to be 55. Folks, 55. W equals 55 is equal to 0. And so if our normal force is then equal to W cos 55, we can then find what our friction force is, which is just going to be our normal times mu. So our normal here is W times cos 55. times mu. Now we can start subbing in some values here. 440 pounds, post 55, 0.4, 100.95 pounds. Okay, so we've got a friction force now. So now we can look at this and think, okay, so the people are going to be at the top here, moving down to the bottom here, A. They're going to have some amount of energy. There's going to be a whole bunch of energy in this system. And I guess I'm jumping ahead a little bit. There's two ways we can go about solving this. We can solve it through energy by thinking of how much energy do we have when our people are up here with some potential energy, and then they slide down the roof. They're going to lose energy to friction. They're going to pick up speed and have some kinetic energy. The bones are going to go up. They're going to have some kinetic energy. They're going to lose potential energy. So we can do this in both of these different directions. So, or both of these different methods. So let's start with energy. So then the other thing we can recognize too is when this is at the bottom configuration, if each of these pulleys here is 8, our position here, we've got 8, 8, and 8, and 0. When this is all the way down, the position, and all of these are up, and all, then SB is all equal to 0. SA is going to be 3 times 8. So SA is going to be equal to 24 feet at the final configuration. So for our energy, we're going to have the energy of the system when the people are at the top is going to be equal to the people at the bottom. Okay, so let's list out all of our terms and then we'll see which ones we actually are able to solve for, or which ones actually have a value, I mean. So we have our potential energy of A at 1. We have our kinetic energy A at 1. We have our kinetic energy E at 1 plus our potential energy E at 1. This is going to be equal to our potential energy B. And so at the bottom here, we're not going to have any energy in A. We can recognize that right away, but we're going to have some potential energy when our bones get lifted up, plus our kinetic energy of our people at the bottom, plus our kinetic energy of the bones at the top, plus, and this is the one to be wary of, energy that's going to be lost to friction. There's going to be a bunch of energy, this potential energy of it sliding down, a bunch of that's going to be lost to friction. Like I said, it says it starts at rest, so the kinetic energy is going to be 0. Potential energy of the bones is going to be 0, so we don't have any of these terms here. Okay, so now let's figure out the energy of each of these terms. So we've got 440 pounds. And this is this term here. Maybe I'll do this off to the side up here. Potential energy is equal to mgh. And m times g is also weight. So I'm just going to sub in the weight in pounds times the height. So that's what this is here, 440 pounds. And then we need the height when this distance is 24. So we need sine 55 times 24 feet. Okay, for our bones, these weigh 650 pounds. They're going to be lifted 8 feet. For our people, we're going to have some kinetic energy here. So we're going to have 1/2 the mass, which is going to be the weight divided by gravity, 440 pounds. Don't forget this, divided by 32.2 feet per second squared. So that's going to give us their combined mass in slugs. And we have some final velocity squared. Plus 1/2. Same thing with the bones, 650 pounds divided by 32.2 VB2 squared. Plus our friction force, which we already calculated. Just going to round up to 101 pounds. Times 24 feet. Okay, now we can do some math, solve this all out. Make sure I've got enough space here. So this far term is going to be 8,650.25. It's equal to 5,200 plus, whoops, 6.83 VA2 squared plus 10.09 VB2 squared plus 2,422.8. So I'm writing this all really small here because I'm only got a couple lines and want to finish it on this sheet of paper. So we did it at the beginning. I'll pull it down here. We already have a relationship up here for VA and VB. So we can sub that in down here for VB2. We know this is going to be equal to negative 1/3 VA. So we can sub that in. This is going to all reduce. We're going to get 1027.45 is equal to 7.95 VA2 squared. VA is equal to the square root of 129.2 is equal to 11.37 feet per second. And there we have it. Now, I mentioned at the beginning that we could do this by energy or we can do it by kinetics. So let's go ahead now and do it also by kinetics and see if we get the same answer. So we can do this in kinetics. We're going to have the free body diagram of the fossil. And so maybe just to clarify where I'm going from here is I've got this free body diagram. So if I were to sum forces in the X, I'm going to have tension as an unknown. And I'm going to have acceleration of A as an unknown. I can do my free body diagram for my pulley and my bones, and it's going to give me tension as an unknown and the acceleration as an unknown. So I'll be able to use the relative velocities and accelerations and the tension being constant in order to solve out for these. So my fossil here, I've got a pulley. Pulley's going to have 3 times the tension and 650 pounds acting down. And so the system is not in equilibrium. So the sum of forces in the y in this case are not equal to 0. Therefore, this is a really common mistake. Oftentimes we look at this and say, oh, well, there's 3 tension up here and 650 pounds. So this is just 3t is equal to 350 pounds, but it's not an equilibrium. In this case, it's accelerating upwards. So 3t is not 650. So our sum of forces in this case is mass times acceleration. We've got 3t minus 650 in our forces. This is going to be equal to our mass is going to be 650 divided by 32.2 times acceleration of b. And so tension is equal to 6.73 acceleration of b plus 216.6. Now, I already kind of alluded to this. We're going to have to sub this into the other equation, which is going to have t involved, but it's going to have acceleration in terms of a. But we can change this acceleration to terms of a because we know that's going to go in. If you don't recognize that right now, that's totally fine. You'd recognize that after and be able to sub that in later. So acceleration of b is equal to negative 1/3 acceleration of a. So the tension is equal to negative 2.243 acceleration of a plus 216.6. A little star here. Okay, so now for the people. This is what I'm going to bring back. Previous free body diagram here. And say sum of forces in the x is equal to mass times acceleration. So we're going to have the weight, the x component of the weight acting downwards, negative w times sine 55 plus tension, which is acting in the positive direction, plus force of friction, which is in the positive direction. Mass is 440 divided by 32.2 times acceleration of a. So now for t, we can sub this value in for t. So we have negative 360.43. That's this weight term. Plus, we're going to sub in this value for t, negative 2.243 acceleration of a plus 216.6 plus the force of friction we saw before, 100.9. I think I rounded it up before. Oh well. Plus 13.66 AA. So now we've got all these numbers, and the only term we have here is acceleration. So this is going to reduce down to negative 42.82 is equal to 15.9 acceleration of A. So the acceleration of A is negative 2.69 feet per second squared. So now we have an acceleration, but it said, how fast is it going when it reaches the bottom of the roof? So we can use one of our kinematic equations. We've got velocity, we know the position, we've got acceleration. And so we do have an equation where we've got our velocity squared is equal to our initial velocity squared plus 2 times constant acceleration. In this case, this is constant acceleration times change in position. So in this case, we know it starts at rest, and we know its initial position is 0. So this is just equal to 2 times negative 2.69 times 24 feet. And then we solve this all out. We're going to have to take a square root of this side. We're going to get our velocity is 11.37 feet per second. So here we've done it. Same answer. Two methods. So hopefully one of those methods was obvious for you when you first attempted this. And yeah, it kind of shows that some of these dynamics problems you're able to solve in multiple ways. It can be really helpful, especially if you don't know if you're right. And if you've got a little bit of extra time, you can figure that out. Thanks, and see you soon.